reconstruction analysis. Just to give you an introduction on the capabilities of the software. And we will first start with a few slides about the software and about some general aspects, and then go into our live demo. If you have questions, so the voices are muted, but there is a chat, moderated chat, so you can just input your questions. We will see them, and we can then just answer them during the demonstration if it's relevant to do it already. Otherwise, we can go back to your questions at the end of the webinar and discuss them at the moment. So first of all, I'm Jelle Vlassenbroek, I'm the CTO of Inside Matters, and I will start with some general information about the software package. So I will go to the slides. So Octopus Reconstruction is the first of 3 packages we offer. So it's the idea is that it's scanner independent, so you can use the software to reconstruct data coming from various types of geometries and systems. It's also normally targeted at high performance, so you can use CPUs with multiple cores, multiple computers in a distributed computing module, and also multiple GPUs for large data sets. The idea is also that it comes with an interface which allows you to tune all the parameters, look at the results of your parameter optimization, but there's also a software development kit if you would like to integrate the package into your own environment. So, and we have several solutions, correction algorithms, and also iterative reconstruction, but I will show some of these things later in the demo. The second package is Octopus Analysis. It's mainly suited for porosity analysis. Basically, if you have microstructures and you want to look at the structure like the pores, you can do some segmentation, some filtering, and calculate a lot of parameters about the pore structure to get some information which is more than just visual from your sample. And we'll also give a short demonstration on a foam dataset to show how this package works. And then finally, we have Octopus Visualization. So it can be used for 2 things. On the one hand, to look at your reconstructed 3D volume and do some renderings. On the other hand, it can also be used to look at the results from your Octopus analysis process. For example, you can look at pores and look at the color code based on the size or the shape or the orientation. So that's basically the third package, and we will also briefly touch on it when we discuss analysis. Just very briefly about reconstruction. So there are different geometries, and the most common ones are the parallel beam geometry, typically used at neutron beam setups or at synchrotrons. Then there is a fan beam geometry. It's more used on industrial CT scanners and some medical CT systems, typically older ones. And also the cone beam, which is one of the most common geometries, typically for laboratory-based X-ray CT systems, industrial CT systems, and also some synchrotron systems where you're focusing. Now, regardless of the source, the geometry, what type of system you use, you always have the same steps you have to go through. So normalization, sinogram generation, and then the reconstruction itself. And we'll just shortly discuss the different steps. So normalization, the point is that when you start in the reconstruction, you get some data from your scanner, but often that's just detector information, so you don't really get the data which is necessary to do reconstruction. So what you first have to do is normalization, and what it does is it will remove any effects of your detector or, for example, a beam profile, and can also correct for fluctuations of beam intensity during a scan. And there are some other steps you can do, like filter white and black spots or images. So all these things are typically done in the normalization step. So what do you do in normalization? Typically, when you do a CT scan, you have a whole set of projection images while you rotate a sample. You also have dark fields where you just disable the X-ray tube or just use a shutter for your synchrotron beam, and you don't have any information except for some offsets of your detector. And then the flat field is again with the beam on, but then the sample removed. You also get a profile, and with a very simple arithmetic, you can get normalized images. And in these normalized images, normally you have a value between 0 and 1. And 0 means that all the X-rays or radiation is blocked, and 1 means that all the X-rays or other radiation is passing through the sample. So that's basically what you get. And once you get the normalization, you go to sinogram generation, and it's just something we do because sinograms are very easy in reconstruction. If you have a parallel and fan beam geometry, one sinogram will give you one cross section. And basically a sinogram is just taking all the information from one detector row over the complete scan and putting it in one file. So it's a bit like the scan history for one cross-section. Now, one sinogram is only equal to one cross-section in fan and parallel beam. In cone beam geometry, you need multiple sinograms for a slice, but again, it's a very interesting structure to do reconstruction. Helical cone beam, something we won't touch upon in this webinar, doesn't use any sinogram generation because it's not relevant anymore in that geometry. Now, once we have sinograms, we go to the reconstruction, and of course, it will be the main topic of the demo. In the reconstruction, typically the point is that you have a lot of parameters which you have to adapt and optimize. So basically, you will reconstruct the slice, look at your image, and then do some back and forth optimizations to look at geometry parameters, artifact correction parameters, select some things about data output, and so really putting a lot of parameters correct, and then you can reconstruct the volume. So these are the general things I want to touch upon, so I will just briefly walk through one data set where I will show all the steps, and then when that's done, I will pass the word to my colleague Jan de Wankele, and he will show you how you can use Octopus analysis for 3D analysis. Okay, so I will start the program. And then I will select the data set. I will use our wizard, and our wizard is just a way to bundle different steps in one process. So you can do all the steps I will show manually, but the wizard just makes it easier to do it without too many user interactions. So I will take this data set. So once we select the data set, you get some information like the number of projections, the number of flat field images, and the number of dark field images. So you can check it and then just accept it. Then you have some reconstruction parameters. If you use, we have a certain type of text file with all the parameters inside. If you use that format, then it will automatically detect the parameters. Otherwise, you can select them here. I already have some parameters from a previous reconstruction available, so I will just take that. And you see this is a cone beam dataset, and you have a lot of different geometry-related parameters. But if you don't know these parameters, a lot of them can be optimized during the reconstruction process. So I will just accept it. We can crop the images, but the sample is centered quite nicely here, so I will not do it. You can use a spot filter to remove white pixels, but the images here are already quite clean. But for example, if I would take a high spot filter, you do see some effect, but it's quite clean, so I will not do it in this case. You can use a region to normalize for beam intensity fluctuations, and then you just take a region where there's no sample inside the field of view. What you see here is some kind of a summed image of all the projection images. So if you see white space, it really means that the sample doesn't enter that region. You can use a ring filter. Typically, the ring filter is a bit experienced, but typically we use filters level between 1, 2, or 3, depending on the severity of the rings. And then sinograms, it's a parameterless option. It will just make the sinograms. So once I put everything in place, then I can start the process. And you can also look at an image. You also see a histogram of the image which is now being normalized. So you can check if it really goes up to 1. And you can also see how much absorption there is in the sample. And then the sinograms will be generated. So now after this is done, you can go to reconstruction. You can also look at the images if you already want to check them before you do reconstruction with a viewer. For example, you might want to check the sinograms to see if they look normal, and then you can use this program to look at them. If everything seems to be correct, and then you just select the correct geometry, parallel fan or cone beam or helical cone beam, and then we take the sinograms which were generated as input. We have an output folder for reconstruction. I already have some previous images, so the program asks if I want to remove them, so I will say yes. and then the reconstruction module will open. Show it in big here. And of course, typically the first thing you do is just see with the default parameters if you reconstruct one slice, if it looks okay. Now here it's quite okay. The center of rotation, it can either be set a priori in the dataset settings, or you can also let the software detect it automatically. In a lot of cases, it's not always that good. For example, you could end up with something which looks a bit like this. And what you then can do is you can use a semi-automatic method to find the correct value. Just right-click with your mouse on the value, and then there is this routine where basically the parameter will be scanned around the current central value. And then you can, if you click it multiple times, it will always do to the narrow search interval. And you can select it, for example, check it, click on an image, see in the big window how it looks, or just look at the standard deviation curve, which typically has a maximum at the optimal solution. So that's center of rotation. It's always the first parameter you want to tune. There are some other misalignment parameters like tilt and skew. Sometimes you can also right click and optimize them, and sometimes you can already have an effect on the central slice. If not, you can just select the slice which is, let's say, for example, completely at the top. First look at one slice, see if it's okay, and if you're not really happy with it, you can also, for example, optimize tilt and skew. For example, here I could just check if optimizing the tilt has any impact. You wouldn't think so because you don't really see it on the image, but let's just have a look. And you can see that even here a very small tilt is in fact detected, but it's really very small, so you will not see it on the image quality. So these are the geometry parameters. There are a lot of different parameters. If you're wondering about what they all mean, they are described in the manual with some drawings, so you know how you can tune your parameters in the software package. There are some more general geometry parameters which you can always check. For example, the source detector and source object are very important if you want to have the correct voxel size calibration. And then you can, for example, if you taken the wrong output folder, you can select another reconstructed output folder even after the program is started. There are some other things, like for example, you can tune the noise filter. If you have 0, it's just a ramp filter. If you increase it, you will remove noise, but you will also remove some sharpness. So basically, it has to be handled with care. You can also, for example, disable the logarithm and disable the filter if you have some pre-processing data, but that's not something which we will have to do here. There are some other things, for example, the ring filter, which is a bit more advanced than the one which is done in data preparation. Again, you can try it on your data and also find some more information in the manual. You can also check for beam hoarding, for example. I can go back to a central slice to see, but of course you probably already saw that this sample doesn't really have any beam hoarding. If you look at the profile to the sample, it really is quite flat. So because it's a plastic sample, it doesn't really have any beam hoarding problems. But if you have it, you can just use a simple beam hoarding correction and put some values here. There is also some options for phase contrast. Typically, for phase contrast, you have a pre-processing step, but sometimes you also want to do some things in the reconstruction, and these can be handled here. And here, the system tab sheet, for example, gives you information about do you have enough memory to do your reconstruction, and if you don't have enough memory, the program will do the reconstruction, but in multiple steps. So normally you don't have to worry about that. And also, if you have GPUs, which I don't have at the moment, you will see it here on the bottom. And you can also select which GPU you want to use. So that's basically it. There are some things about the output format and the scaling, but I will not go into detail here. I think it's a bit too advanced for the first webinar. So I will just proceed with the reconstruction. And just one tip, if you have a small data set, it's best to disable this visualize option because it can really slow down everything. And now I have to wait a little bit, so if there are any questions in the meantime, feel free to ask them. Otherwise, we can proceed after we have reconstructed volume. I will already also maybe open visualization program, because as I said, visualization can be used on the one hand to look at the 3D volume, but also at analysis results. So I'll already open it so it's ready when our volume is reconstructed. Just one note, reconstruction takes a bit of time here because it's not really high performance laptop, but if you have big data sets, we would strongly advise you to use GPU or a good multi-core system. I see that we have one question about the phase contrast module, how it is best to use it. Now, phase contrast is typically something which is for a large extent pre-processing. So you have two different algorithms which you can use. One is called the Parnay algorithm. The other one is the Bronikov algorithm or the modified Bronikov algorithm. These you can use just to do first, let's say, to remove the phase or will extract the phase from the images. There's also another approach, it's called the bug correction. It's based on Bronikov, and it's typically something which you do on the one hand in pre-processing, but also then afterwards in the reconstruction. But it's a bit, yeah, it's something which we can best show on data showing phase contrast. So the data I have now available doesn't really have phase contrast effects. So I think it would be something we can, for example, follow up in another webinar on a more advanced topic. So I think maybe, yeah, it's one more thing to do. So I still have to scale the volume correctly. This is something you can do after reconstruction, but also beforehand. I will do it now. The scaling module is just to make sure that all the images have the same grayscale level. Otherwise, if you load them in visualization, it would like be different gray values depending on the height. So I will take a look at the results in our visualization program. So we can load it here. We also have some options to do some alignment. For example, I'm going to change the mode because the sample which we scanned here was not put up right, so we have to change it a bit. Just rotate it until it's correct. This is about correct, and then in this direction. So basically the visualization allows you to look at just some slices, but you can also look at the object in 3 dimensions, and you have some different rendering modes, for example volume rendering, and you can just quickly go into find some settings where you get a pretty good image. You can change the opacity. Optimize the gray values and even apply some shadow, but it slows down a little bit on this slow laptop. And then you can also rotate it. So it's let's say it's a good solution if you want to, after reconstruction, want to have a first visual idea about the sample. You can take a look at it, and you can also play a bit with things like filter settings and rendering options. So that's one of the things you can do with it, and then afterwards, if you have a sample report, you can also use it for looking at the results. So I think those were the things I want to show about reconstruction. So I will now pass the words to my colleague Jan. He will show you the analysis package and go through a workflow there.
Good afternoon, everybody. My name is Jan de Wankelen. I'm responsible for the services at Insight Matters. And Jelle already showed you how to reconstruct the data set and to visualize, to gain some first insights in the 3D volume of the reconstructed data set. So what I will show you is how to analyze a data set. That is important to become, besides the visualization, also numerical information about porosity, about cracks, about different kinds of structures and textures. And I will show you the basic steps we do to obtain data from a pore size distribution in a foam data set. So the first thing is I will open Octopus analysis. So we will analyze the pore structure in a foam data set and try to obtain some results about the porosity and also the pore size distribution. So when you open the program, you have several options which you can adapt. The threshold options, the storage options, and all kind of other options. I will leave the settings like they are now. Accept. So the first step we have to do is open the folder we want to analyze. In this case, the foam set. So if I choose the folder, it will open all the different slices. So on the left hand side you can see the different slices and they are visualized in the center of the program. So second step is I select all the images I want to analyze, because now they are still in a 2D setting and the goal is of course to have an analysis in 3 dimensions. So we load all the different slices. I go to Tools, Load Volume. And then in the next step we have the possibility to change the region of interest by selecting a square, but I will leave it off and I will load the whole volume. Enter the voxel size, press OK. So now all the slices are loaded into the program, and if I go with my slicer you can clearly see the foam, which is white, and the pores, which are black. I can slice through the images in the Z direction, but also in the X direction and the Y direction. So to start with the analysis, the first thing I have to do with this dataset is to filter it, because you can see, as you can see, there is some noise, and if we want to threshold, it will cause some problems in the threshold step. So I go to filter, and then I will use a median filter. Okay. Accept. So it's not always necessary to filter your data. It depends, of course, on the scan, if it's necessary or not. But in this case, it was obvious that we needed to use a filter. So now that the data is filtered, we go to the threshold step. So the threshold step selects the features we want to analyze. So in this case, we want to analyze the porosity and also the pore size distribution. So we have to select in red the pores inside our volume. So I can, as you can see, move the threshold, and then we try to find the value that indicates the pores inside the foam. Press OK. So now we have a binarized volume with in white the pores and in black the foam structure itself. On the binary image we have the possibility to perform some binary to binary operations. It's visualized on the left hand side, so we can shrink a mask, close a mask, fill holes, remove some isolated voxels, some background voxels and foreground voxels. I will leave it like it is now. And then on the right hand side you can see we have some analysis tools. So we can already perform some analysis on the binary image. For example, I can calculate the partial porosity in the z direction. So if I enable this function and I press calculate, the program will calculate the porosity in function of height inside the sample. This can be seen in the datasheet. So if I go to the datasheet, everything we do during our analysis will be stored in the datasheet. So as you can see, I entered voxel size 15, it's stored in here. Also the region of interest we selected, the threshold mode and the threshold value, and then we can see the total porosity and the partial porosity in function of height. So from 0 to 10, from 10 to 20, and so on. So afterwards we can export this file and it can be opened with Excel. If I go back to the volume, we're still in the binary data set. So in order to have some information about pore size, we need to do some additional steps. And the first step is the labeling step. If I press OK, so now the program will define which objects are connected to each other. And as you can see, there is a very open pore structure where all the pores are connected to each other. It's all green. So we can obtain some information about that structure, but we want to have some information about the individual cell structures inside the foam. So I need two additional steps to do so. So the first step is I will calculate the distance. So now, if I calculate the distance for each voxel inside the pore structure, its distance is calculated from that specific location to the border of the object. And then you get an image like this, within bright and very white are the voxels located very far away from the border, and if you go towards black, so very dark gray, we have voxels belonging very close to the border of the object. In the next step we can separate the objects, so the separation is based on the distance transform. It's a watershed separation. And then I have the possibility to calculate some additional parameters, the minimum closing, and also I can determine the connection. So in this case we only need the equivalent diameter of each pore structure. I press OK, all the pores will be calculated and separated from each other. Afterwards we can evaluate, we can see if the program has defined each individual pore structure correctly. And if we then press OK, it will complete the separation. So as you can see, the program found 102 individual pore structures. Of course, in reality, those pore structures are connected with each other, but to obtain the information about the size of each cell, you need to separate it. Then the program asks if we have to remove the objects connected to the border. I would say no, but sometimes it can be important to be sure if you have the whole pore structure inside your field of view. So if I scroll through the complete data set, you will see now that all pores are separated and they are all labeled as an individual object. So now they have random colors, but in the next step, the classification step, we can select a couple of parameters. And the first one is the equivalent diameter. It's the diameter of a sphere that is composed out of the same amount of voxels as the pore structure itself. So if I select this and I press OK, the program will classify all pores according to the equivalent diameter, with in red in the center the biggest pores, and in blue below and above you have the smallest pores. Also, this data is reflected in the datasheet. So if I go to the datasheet, you will see that all the information is stored as well. So here you have a data list with the equivalent diameter, where you have several columns. It identifies the equivalent diameter. So for example, if we show on row 60, there are 5 objects with an equivalent diameter between 150 and 120 and 150, with a middle 35 micrometers. They have a volume of 1671 voxels, and there the volume is given in cubic micrometers. So in that way we are able to obtain a pore size distribution curve from the data over here. If I go back to the volume, I can show you another classification. For example, a classification of, let's say, the sphericity. How spherical is my object? It will be given in a value between 0 and 1, where 0 is a very irregular flat object and 1 is a perfect sphere. So click OK. Also in this case, the data is relabeled with in red the spherical objects and in blue the more irregular objects. So in that way we can obtain a lot of information, numerical information about our volume. Of course, we also want to visualize the pore size distribution. And how do we do that? We can, as I already mentioned, we can export everything. So we can export the images, the individual images. We can save the spreadsheet, but we can also save the object data. So if I select this, all information is stored inside the object data. I'll make a new folder. I'll call it webinar. So now to visualize the pore size distribution, there is a small button over here, and it automatically connects with the visualization, with Octopus visualization, to open the calculated data. We'll open this. It will ask to open the dataset. So I select the folder. And now you can see the program opened our analyzed data. So I will tune it a little bit. I will put the resolution on very high, the quality also on high. As 3D view, I will use the volume rendering, and I will use the auto to put some color in it. So now you see again all the pores have a different color. In order to classify it in 3D, we go to Octopus Analysis on top of the program, and then we can change the parameter. So if you go back to the equivalent diameter, if I click on it, the program recalculates the gray value for each pore structure, but with a gray value that is reflected in the analysis results. If I press auto again, you will see that the big pore structures are shown in red and the blue ones are very small. Another example, if I go to sphericity, for example, I go to auto. Okay, so now in red you will see the pores that are closest towards the sphere, and blue the pores that are more irregular. And then, for example, we can rotate the volume, or we can fit a clipping box around and really cut through the volume and see what's inside. So that's basically the main workflow of how we work with Octopus analysis. Of course, it's a very fast and very basic step we've done, but it can be applied on all kinds of different materials and on all kinds of different structures and textures to calculate images and parameters. So we'll have a check if there are questions on the part of Octopus analysis and visualization. If not, we hope you liked the webinar and the Octopus reconstruction, analysis and visualization. And of course, if there are questions, you can always send them to us privately via email, or if there are features requests or other comments or thoughts, you can contact us. So again, I hope you liked the webinar, and hope to see you again in one of our next webinars. Thank you very much.
Thank you.